Hello, everyone. Welcome to today's seminar. Today, we have a speaker that is called Takashi Sukagawa. He comes from the Canon company in Japan, and he's going to explain different developments they're doing. But just as a brief introduction, so you know that the IAC, it's a world leader in the development of instrumentation. In particular, in the case of solar physics, we have been in that position for more than 20 years. And one of the things that we did first was to integrate and offer to the community an spectrograph, but with an input as an integral field unit based on image slices. We have been offering to the community this instrument since 2019. And the idea is that initially we did a development with a certain slicer width. It was 100 micron. And the idea was first to prove that the technology was possible to be applied in solar physics, always thinking to apply it eventually to EST. And then in that sense, after proving that it worked, the next step was to try to make a prototype with a slicer width that was similar to the one that we need for EST. And in that sense, we needed to go to a slices of 35 micron. And so far, the only company that has been able to provide such technology is the one that we have here, so Canon, and the team led by Sukagawa-san. And the idea that we would like to continue not only making the prototype for EST and installing it here in the observatory, but also to eventually make the instrument for EST using this technology, but scaling it to the proper size of the instrument. So I think Sukagawa-san will explain some of these technologies today, some additional ones. So I hope you like the talk. Okay, thank you.
So thank you for thank you for introduction. So please try to understand in my poor English, but anyway, you watched my slide as possible as you are understanding. Okay. I visited the ISC 10 years ago. After 10 years, so that I make some many optics. Oh, how to move it? Oh, yeah. Oh, this is the introduction. So the 10 years, I'm shipped to many optics to astronomy. So I just introduced first. But at today, I would like to understanding for you for the hour, or no, not only hours, but also the machining for the capabilities recently very nice. So what is some restriction? So you avoiding some restriction. You can make in any optics by machining. So the other thing is just the introduction. So there's some image over some production. So second part is important. So I am first, okay. So that's I shipped for the one of the major program of the METIS of the ELT. So we Canon ship to METIS primary grating. This is made of germanium. So METIS using the germanium immersion grating high spectrometers. So you can see your left one, this one. Just one. Just 100 millimeters, but the index is 4. This is works almost the same as 400 millimeter larger grating. So that's METIS achieved very good high resolution spectrograph. Maybe you know a lot of the publishing. And also this old one, but later than 8 years ago, we shipped to VLT in Chile. The instrument name is Gravity. I'm not sure you know or not. We are upgrading for the gravity for the just changing the algorithms. Yeah, the old one is a US company making that on the zinc selenide algorithms. Traditionally, this kind of wavelengths covered to using the zinc selenide, orange one, yellow one. But we just switched our grating for the germanium. That throughput is 1.8 or 3 times very higher. So Gravity is very happy just to switch the one optics. Their throughput is very huge, big improved. And also, we ship to Colorado as an image slicer. So like that. So the program is LASP. Oh no, yeah, LASP. Yeah, this kind of the EUB slicer is very difficult to make it because EUB is limited of the optics number. So this slicer has not straight. This is have the curved, some powered. So in the past, this is not easy to fabricate with the monolithic pieces. So but machining, you can understand machining is easy to make in some kind of surface. So we ship to that. And also that's DKIST. So this is sort of telescope in Hawaii, Maui. So this is IFU for the DKIST upgrading because DKIST you're using for fiber IFU before, but you know fiber IFU has a lot of problem. As some lack of some performance of the throughput or something. But now changing the whole instrument for our machine type of the IFU now operate in Maui. And also, the second generation, Oxford, is planned to the ELT project is the next, this is now first one, second generation already prepared of the IFU, very funny IFU, I'm not sure. Anyway, they are already using, this is a very funny slicer. This is both curved, meaning a freeform slicers and then operated. So you can published by Oxford, you can read some papers. So now Canon is involved to VLT is still very big telescope in Chile. And the ELT also now construction, as you know. And the KECK, already we shipped to KECK telescope to US project to the Western university, something using KECK project. And also DKIST in the Hawaii NSO program is involved to award optics. This is our production, introduction. And also, now we I touched with UB waveguide. This is now machined. You can see, yes, UB waveguide is important for the next generation of the high sensitive spectrograph. So that we works with Max Planck, the Henshu-san is, he get a Nobel Prize before anyway. So this main part of today. So Canon is we are camera or something, some kind of the company made of the ourselves. So we are traditionally making our original machine in our house. But this machine itself very familiar with you, any machine has the same configuration, X, Y, Z, and some rotation. So that's just different of the some accuracy, absolute accuracy is different of the commercial machine. So you can see global, meaning of the any place. Well, our stroke is usually 300 millimeter, 300. Yeah, and any scale has an accuracy of 55 nanometers. So meaning of you say 100 millimeter plus minus 55 nanometers. So meaning you can get any place you expect it, peak to valley of this number. Yeah, and also that's position. As position is important short term. Every machine, we can guarantee the 1.5 nanometer. This big, very important number for when you machined by grating. Grating of each can be machined, every commercial machine, but of course we want to achieve good diffraction efficiency. This kind of accuracy is very important. 1.5 nanometer is usually very enough to using for the visible light wavelengths. More shorter side. And also angle accuracy is important. Grating should be very parallel, of course, so that we can guarantee it of 0.001 or 1 second or much more small number. We can guarantee any angles. And also important, please understand, surface micro roughness is less than 1 nanometer, just machining, no post-process. So I show you next slide. But anyway, so that accuracy can be achieved, this kind of very small, meaning large groups, 50,000, meaning the pitch is 20 nanometers. 20 nanometers scaling can be machined because of we can guarantee this kind of accuracy. So you can see it looks like very parallel, very line, isolated line. So if you try to in your house machine, you making this kind of pitch. You cannot isolate it. Usually, I'm not sure. You try it. So, no, this is nothing. Yes. So sometimes I talked some kind of presentations, sometimes misunderstanding. So I try to make one slide. Our machining is just machining, meaning no need pre-process. Some grinding, something is no need. Just prepare, just work. And we just machine, yeah, like that you want. And no need post-process. You never no need to the polishing something. You can achieve surface quality of optics. So you meaning that you're mechanical designer, something, or optical designer, considering about some kind of funny shit. You don't care about pre-processing and post-processing. You can understand it something, oh, it looks like making the machining center or some machine. Okay, you can achieve you can get the optical device as you like. So that's very nice surface, very nice edge. When we guarantee to for example, the grating requirement, the edge quality is less than 20 nanometers, very sharp edge. So, and of course, this, after machining, we usually do coating for the high reflectivity, of course. And other parts, when we're making the generally, and no requirement to end the customer, we ship to this kind of structure like that. This is using the DKIST IFU multi-phased mirror. This is 112 monolithic integrated mirror. But what kind of structure we providing? Usually base material, almost 99% as substrate is imber. This is metal with rod thermal expansion. And the top on the top of the imber, we are plating. This is because copper plating is the usual or better for the good machining quality. Of course, we can machine or the copper, aluminum, something, because same as a machining. So, but no, this we recommend of the disc structure, copper layer, it is small thickness. So usually you can expect it, low expandation is base material. And also we machined this layer for some kind of like that. So you can see a copper color on the surface of the optics. And also that we are put on this after the machining, the reflective layer, meaning just coating the aluminum or the silver, gold, something. Yeah. And this is no need to explain for you, but generally this is not so special technique. This is a machining, is a two type of the shaper and the fly cutting. Shaper is very simple, is moving just the tool, one direction. Yeah. And the fly cutter is very faster. Maybe you can see here many machine. Yeah, this is not so special, but important. If this machine has very high stability of the edge of a tool, you can machine the single point. Single point meaning tool has very high stability, almost 2 nanometers, something, 1.5, I said. Yes, you can machine the very small area. Many times you can cut in, you can make a very complex surface. So we can provide to Oxford completely free form image slicers. So not because of the free form cannot make in the tool shape. Diamond tool cannot make in the free form. So that, but this technique can be allowed. You can want any surface, very high order surface. This can be fabricated. No, because we no need post process. I mean, we don't care about the polishing. Yeah. And also this is very important, uh, but poor drawing. But I explained to NASA last year. They understand it maybe. Okay. Anyway, so this is a very traditional machining. So not so special. So please understanding, this is some restriction. So tool must be passed away to our target. So we cannot cut in like that structure. Of course, this direction impossible. We can cut in this direction. So easy to know. And also you can make in some space. Yeah. So we can cut in this direction also. This is very important. And also the traditional 10 years or something very old, our image slicer makes tool itself, very small tool, and just machining the one direction, very easy. But recently, the end customer requires not a flat surface. So we say single point machining. But we can, like that, we have to make that shape. The tool has a wise, of course, very wide, big wise. So when we cut in like that tunnels, we have to flip something like that. But you can image some kind of flip or something, meaning of no tool interaction. We can make in the machining. So meaning when we machine, this surface is optical quality. Yeah. And also, the other problem is we want to keep in the very constant speed. So very funny, very structure, meaning this kind of point is we have to do some break, need acceleration again. It's not so good quality for the machining. So in such case, please understand some optical designer or machining designer can be makes some kind of the isolation place very slightly wide, not so much space as required. So anyway, this is a restriction is the same as usual machining. But if you can image your optics or machine, okay, the device is satisfied this or avoiding this restriction, you can make in any, not a flat, any 3D position can be made in the optics. So, so this is one explaining. This kind of looks like some complex multi-faced surface, monolithic mirror, but you can see we can cut in this direction and slightly isolated of each column. So we can make in this kind of optics, the one pieces of our machining. So, and also single point diamond cutting is allowed. This kind of shape is easy because in, out. So no restriction. This kind of shape is very happy for us. Anyway, so important for the gap is not much more smaller is okay, but we are very happy that's gap is 0.5 millimeter or large. Of course, we can negotiate. That's what come from this number. We can allow, meaning a lot of time, allowed to, we are very slowly machining. Of course, this gap can be much more small, 100 micron, maybe possible. But anyway, nobody wants the very high cost. So meaning with the maximum speed, we are operated. 0.5 millimeter is very enough to spacing. So it's important. How much, why not we choosing the copper plating? Yeah. We are very nice machine, we believe, but the surface quality is not to depend on only our machine quality, but also the material is very big influence. So that's copper, you can see, just we are machining. You can reach, I say the 1 nanometer RMS or below, But this data is not so by chance, a very popular number. You can get in a very nice number, 0.4 nanometer, meaning 4 angstrom. Yeah, like that. Yes, peak to valley is still small. But when you want fabricate or machined by germanium, we ship to ELT metis, germanium grating, something like that. Still no, not bad, but something larger because of a different of the material. Germanium as less than 2 nanometer is currently guaranteed number. So that's not only the SIP2 METIS, but also the Caltech. They are using the KECK telescope. They funny reflective grating is made by germanium. In past, never to using the germanium substrate reflective grating, but Caltech want to keep high stability of the material, meaning they want to using single crystal. They are very sure shrinking in the low temperature operation. So US people are choosing the substrate made of germanium. It's very new. Anyway, so they are publishing in last SPI in Yokohama in June. You can check the papers also. Anyway, so many application. So especially European people asking us for the aluminum. Yeah, RSS 6061. Yeah, this is very popular. I'm not sure. But this is aluminum. It's not a crystal, of course. So this is not so good for us. We are machining. This achieved this kind of number. Still not so, but still not so good. So usually we recommend some structure of the 2-page previously. Yes, invert, copper plating, glass machining, and coating. It's very much sure. Of course, you want to shrinking something. For the all instruments made of the aluminum, of course, we can machine by aluminum directly. But not expected to perfect number of. Okay, but the infrared using or something is okay. So we can ship the many type of the device, but you can understanding this of all of device was satisfied with our machine limitation. Yeah, grating is you can easy to understand it. Grating is very open space. Yeah, one direction, so no restriction. And also this kind of funny grating also. This is a column, but there is enough spacing over the 0.5 or something, so we can make it not only the one piece of grating, but we are multi-phased grating also, machining on the monolithic. And also this kind of introducing. And also traditional image slicer is easy, both of the open space. And also I say the waveguide also. Waveguide is right in, right out, meaning we can pass the two right in, right out, meaning we can machine, not only straight, but also you can see funny shape. This is the interaction or the splitter. Yeah, waveguide is important. Splitter, the combiner, something. And the focusing is function is involved this waveguide, of course. So, and the next is the importance of the global accuracy and the position accuracy in our house machine. When you machined of the large piece of the grating over our one stroke, for example, this is a 360 millimeter large grating. Our machine is one axis only 300 millimeters. So when we machine such kind of large grating, not flat, some kind of the 3D dimensional, yeah. So mounted one direction, one X, Y, and both of us we combined machine to the 1.4 times larger grating area can be machined. My message is we prepared, we machine to 2 pieces because some kind and the customers want to mosaicing 2 or 3 grating, but they all want to use in the almost same face grating is required. So that we can make introduce into 2 different. So you can see a slightly different face but the number of some number is same. It's very special for, this is a UV, ultraviolet grating. So this requires very nice number. This is high order surface flatness. This is maybe in the 632 is operating the 100, maybe 400 something anyway. Yeah, so you can see 6 nanometer RMS. Peak to valley is 32. We are guaranteed global positioning accuracy is 55, I told you. So this is almost, of course, reasonable number for us. Yeah, so that is now we recently in past scientists, astronomer using the replica grating. But this number is much more better. And also you can get in 1, 2, 3 pieces, almost the same face. So say something, Canon is happy. Some end customer want to use using the mosaic grating order to Canon. So this is the main topics all over them. So very quickly, but so just inform to very additional. So in past, ruling, yeah, Richardson and Newportson is very king of the grating. Yes, very nice. But the group number is very difficult because their ruling engine is very slow. So there's such kind of view for the French company is making some different technique, yeah, etching or something for the interferometric technique, lithography. So that's very nice because a high number can be achieved or making 400, 4,000 something. But the surface roughness is no good. So hybrid is recently Japanese company or some company released holographic and ion etching or something. But anyway, we cutting is very good, something like that. Of course, still cutting the problem is we can make in the each groups by machining is not so good for the small spacing. But fortunately, the shorter wavelengths is required not so much, not large grating. So we providing recently EUV grating also because small piece is enough resolution. So that's different. That's important informed. You can see before, so Richardson is a very, very nice company, but ruling meaning a pushing of the material. So that's, and of course they can make, they have to make of the replicate because they cannot use in the master because master, this bottom is pushing something very big defect. So they have to odds replica using, meaning of the nice edge of the apex areas. But you can see still, yeah, I respect Richardson. They are focusing here, group surface, meaning braze angle, braze facet is important for the grading. So their quality is very, some kind of nice. But you can easy to know that machining is removed of the old material. So you can shape not only the braze surface facet and the counter facet, also very nice. Some character of the polarization, very good agreement of this kind of shape by calculation. Yes, so and also other technique. Shimazu-san, Horiba-san, with a French company, is some etching has very big impact of energy. So you cannot get in the not high quality surface. This is not a simulation, sorry. This is the AFM measurement. So it looks like very, yeah, some kind of, but the Canon case is not so, yes, very fine. So I say, show much more detail here. Yes, Richardson is very nice. So, but they are focusing on this very primary important phase, part of the grading. But anyway, we can make it like that. And also, yes, so this is a much more high, big image, but still you cannot so find it difficult to some defect. This is a measurement, not the CG, computer graphics, but this is very small pitch, 200 nanometers. So recently we provided EUV, shorter wavelengths grating also by machining. So, and just the summary of the gradient of the you can use it. I already say the GRISM is very traditionally many spectrograph using GRISM. So we are providing. So I talked about the VLT gravity using our GRISM, and also METIS also we using the GRISM also, master grating also. And recently we any high-end instruments using the infrared grating is immersed grating is very popular. So that's now immersed grating covered 1 micron. This is important. 1 micron to 220 micron in Canon. Yes, 1 micron is using the not the germanium. That's we using the indium phosphide. Very not familiar with you, but anyway, this is we providing not only astronomy but also physics. Physics where communication team is required 200,000, 300,000 high bringing power. This kind of immersed grating is 3 or 4 times very compact, meaning the surface or the image quality is very nice. So usually the physics guy has no choice because the student can be making the spectrograph himself. There is no knowledge about that, but very compact is anytime easy to control the aberration. And also, this is very common traditional grading. And also just informed. We not only direct machine, meaning we not only ship to the master grading, but also you need 100 something. We making, of course, duplicate, copy the grading, same as Richardson. We can ship to also. So just informed again. So indium phosphide is not familiar with you. German is very famous. German covered 2 micron too much, some 10 something. And not maybe this is only the space mission. Cadmium zinc telluride is covered much more longer wavelength. So meaning, unfortunately, solar C is not mounted this kind of grating, but some future mission is using this kind of grating. Anyway. So, and also just the introducing of the machining is very allowed. Oh, sorry, machining. Okay. Oh, 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 okay. Oh, 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 hold on. Oh, oh. Okay. Anyway, it's okay. So, oh, 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 oh. Yeah, I just want to say, that's kind of accuracy, absolute accuracy is a very nice number is 8%, 80%, something familiar with just the traditional grading. But okay, this is immersed grading. But I want to know that this kind of 500 micron is a huge big groups in immersed grading. This is operated 1,000 orders. So this is the physics guy is usually operated not only the Japan, but also the, for example, the very Princeton, US. Well, anyway, and Colorado or something, you can find out some paper. The physics guy is operated 1,000, very high resolution mode. But this kind of big number is required very high accuracy, but still achieved. Probably very nice efficiency, please understand it. And also this is, if recently any spectrograph is diffraction limit is required. So that's this kind of grating performance important, not only master grating, but also the isolated GRISM, something like that. Okay, anyway, so do you please understand it? This is a number, actual number with a wave front area is less than 10 nanometer or MS. Media, but just kind of same as much more better of the reflective mirror. So you can design to the diffraction limit spectrograph. That kind of performance is very important. So there's no need so much times, but then this is our first work, 2014. This is an image slicer. Wise is 30, sorry, auto slide show, sorry. 30 micron, a small one. As this is machining. It's very easy because what 20 microns is possible. So just the machining. Oh, sorry. How to stop this kind of anyway. Uh, okay. This is a history. Okay. I try to quickly. Okay. Anyway, history. So the first one is 2014. So the many end customer noticed there's possibility the machining is possible to much more number or much more complex shape. So the we ship to this is a DKIST. This is a slicer number is 112. Yeah, and also the some spectrograph required not so much number, but much more small wise. So we ship to 20 micron. 20 micron slicers, but the number is 84. And not of secretness, but we now making latest one is 20 micron, 380 face, very small, very complex for the drone application, something. So you can see in the near future, drone using the integral field unit two-dimensional real-time spectrographs. Yes, not a satellite. Anyway, so this is a very new challenge last time. That's Oxford is using freeform. So now you can make in any shape and integral field unit of not only the slicer, but also you are correcting mirror, something. So many of the like that because sorry, this no your IFU team, but when you divide it after the slicer, the beam is a different number of the 100 something. So after that, slave meter is same number as required. Yeah. So you are very difficult. Only the slicer is monolithic after that. But nobody want to make an alignment of the 100 mirrors accurate. So after that, slave of the slicer, of course, slave mirror also the making the monolithic. No need adjustment. So very high accurate. So this is a curved mirror. So now don't care about the flat, curve, freeform. We can possible to make in that. So very high quality of the beam quality of the image. So it's important is just 20 micron is very close of the CCD, the pixel size, or 2 or 3 pixels. So meaning image quality is very important. So that optical designer should be carefully calculate to the very free form to achieve the image quality. In past, it's impossible. You can calculate such kind of funny shape, but now you can possible to make in any shape. So the last one is interesting. This one, okay. Of course, in past, grating is a monolithic piece. So you using the three grating, you have to install the three piece grating each of each. But now you can integrate it grating. So that this is 6 grating, very different angles. Yeah, this is I told you already. So some drone system is not only the complex slicer and the mirror, but also grating also some many channels. So we can provide in such kind of monolithic grating also. And also the immersed grating also recently the 3 combined immersed grating. Not only one piece, it's 3 pieces also. So this is show you the no need to explain. But anyway, DKIST is now switched to the fiber systems. Same configuration, same compact space, but 112 the continuous mirror meaning much more better image quality of the fibers. Anyway, for the DKIST, one NSO team is very happy now. So show you some image of the unit. Image slicer, you can see this image slicer is just 2 millimeters square, 112 meters, but you can see it's a very small numbers here. After that, divide it 112 meters. The collector meter is monolithic. So you can listen in not important for you, this systems, but you can image what we can make. Yeah, this is kind of course, flat or curved on the meter is easy to machining, of course. And also there's micro slicers and the integrated meter, the curved grade meter. So this is 4 pieces. combined, making, okay, this is slicer. There's more, not scaling, sorry. Yes, is okay. So this is some presentation already sometimes explained. 4 pieces integrated mirror is housing the basis 3 data plates, just pushing of this direction and the optical axis and also pushing the both of sides. So meaning no need alignment. There's tight screwing. It's finished alignment. No need adjustment. So such kind of very nice reliability is not the use on the ground-based telescope, but also the space mission is very happy because high reliability is no adjustment. Yeah, so this is the cross section. You can see here, looks like some complex, but no need adjustment. Yeah, the last topics. So you can see here, just to introduce. So the spectrograph is nobody want to destroy light. So our device, except optical surface, we are making a bracketing. So Canon as our commercial camera or something inside. Of course, commercial production also nobody want to destroy light. So we have some technique in Canon of the laser bracketing, laser. Yeah, femtosecond laser is making some metal or some surface. We can make in a bracketing. Yeah, like that. So you can make it not only for this kind of application. So recently we are some touched for the solar sea. Solar sea has not provided optics by Canon, but we provide bracketing technology to solar sea in the space mission. Just bracketing, yes, anyway. So you can see a very small number of the reflectivity. This no treatment has a few 5% something. And the treatment is very not see can see. So now we can provide this is of course depends on angle. 5 degree is almost 0.03% something like that. As a wide wavelength dependence, very important. Also, some question is 70 or something high angle is very familiar with Canon cameras inside. So this technique is developed for this kind of angle. So sorry, that's a very conservative number, but you can expect it much more high angle, meaning high reflectivity usually providing, but our bracketing can be achieved to much more nice, almost same number of the very high angles. So no need a summary maybe. Okay. Today's message is now you can make in just machining, just cutting. No need post process, as you can get in any optics almost. Yeah, no need polishing. So that's shape accuracy is maybe very nice number, and not only the optics, but also something housing. So some mount or something assembly unit when we make in our machine, because 200 millimeter plus minus 50 nanometer accuracy is usually not achieved any machine. But you can want to put in a very nice accuracy or data frame or data place. So we can provide not optic, but also some data plate as you can use in something align, something check, something. Yes. So very high, good number. So you just put in some your device is high accurate, just put in. So no need to alignment anymore. Yeah. And also the surface roughness I told you, this is just machining. We can achieve the much more less than 1 nanometer. So you can use in the visible light wavelengths is maybe enough. Recently we developed the EUV application less than 0.5. Some number is already achieved. Much more constantly getting much more good numbers. So next year we are new challenging to try to XUV waveguides. It's much more nice number. So I hope in home to you much more nice number by machining. Yeah, thank you for your attention. No question is welcome.
I have a couple of questions regarding the grating development. What is the maximum size you can produce?
Generally, we provide an officially 380 millimeter length, and width is 150.
Okay.
150 millimeter
150
by
times 350.
Hmm?
150, 350.
Yes. Group area is 380, 380, 150. Yeah.
And the thinnest groove size, it was 50,000 lines per millimeter?
That depends on our limitation of the group width is 200 nanometer or something is possible. But problem is, of course, machining time. So my answer is group pitch is no limitation usually.
Yeah.
But then that's total machine time is a limitation for us. So if you use small one or the UB for the 10 millimeter, we can provide 4,000 grooves per millimeters. But usually larger one is a long wavelength usually. So many of the you are required 10 grooves per millimeter or 100 grooves per millimeter. In such case, it's okay for the largest one. It's possible to provide.
Okay.
And according to my experience, the largest group and the funny requirement from physics guy is 1 millimeter, 1 group per millimeter. Very huge, large groups. Yeah. And smaller is for, it's much, no difficult. Any small pitch is okay.
Okay, thank you. I think you showed also a plot showing the dependence of the polarization.
I'm not sure.
The very beginning.
Oh, beginning. Fuck. なかったっけあれoh.
This shows the polarization. This is the PNS fluctuator. So what is that?
Say.
This one. Not the graph. Not the plot below. The plot below. The plot. The throughput.
Yeah. This is a different of the polarization dependence. Yeah. So, yeah, this is a TE polarization, TM. Yeah. So the big difference of the polarization, but this is a.
So you provide that information about the polarization behavior for a given grating. If we specify a grating, number of groups per millimeter and the coating and all that, you provide that information?
Yes, of course.
Yes.
And also, yes, good chance to explain. This is some complaining to an optical engineer by European team because we recommend, just different, nothing to do with maybe your question. Yes, we can calculate, of course, when you design something, because this is a very conservative design for the same as the Richardson, meaning of the apex angle is 19 degrees. This is no good for that polarization dependence. The one side is usually very low. So that machining is possible to much more small number of the apex. It's very big impact for the polarization dependence is very close. So the different, sorry, your questions, but we of course we provide into that kind of character of the grating. On those also you can achieve the much more nice efficiency, just machined, meaning of small apex angles. It's much more high throughput. You expected usually high order grating is 5% or 6% better than before. Yes. Yeah. Sorry. Yeah.
Thank you.
Another question?
Yeah, hello,
Yes.
I have a question. Can you hear me?
Yeah.
Yes.
Hello,
Hello.
Yes, we can listen to you.
do you hear me?
Yes.
Okay. Thank you for your talk, incredible. I have a question regarding the indium phosphide machining for grisms. And the questions are, which is the roughness you get for that surface? And what is about the size you can get? I guess it's a single crystal, or I have no idea. But and what is the largest size you've worked with those grisms? Thank you.
Yes. For grisms, also same limitation. Grisms also same limitation size. Many of the almost 100, 200 by 200 something is possible to machining.
Okay.
But for my experience with Harmony, some infrared, near infrared required first order is a small pitch, 1 or 2 micron. So in such case, 200 by 200 is in theory possible, but it's very long period required to machining time. So of course we can provide in only one pieces, but maybe or Harmony is required already 4 tiles or something. So we cannot provide it. Anyway, so your question, yes, we can provide in a very large size, 4 inches something, for the algorithms in the effective area can be provided. Yeah.
Yeah, and regarding the roughness, you have a good roughness for gas for in transmission for this surface. Well, I mean, it's not copper, obviously, and you finish on this surface, and roughness is a good one. Scattering is low.
Yeah, that depends on the materials, but for example, germanium is you expected 2 nanometer RMS, both of not only the grating side and flat side usually just polishing. You can achieve much more nice one or much more small number of the surface roughness. Yes, but the grating side also many of the you can expect it 2 nanometers. But the grism is you of course transmittance. So we cannot make it because important. We cannot make it for the usual glass, meaning fused silica or something. It's not good for machining for us. We can provide only if you want to the visible, clear material using the calcium fluoride. Let's see. English okay? Calcium fluoride. Calcium fluoride. Okay.
Yeah.
Yeah.
All right. Thank you.
Thanks for coming. And in 2 Fridays, we continue.